Hello everyone, welcome to our quick little recitation on measuring the speed of sound in air. And we are going to do that, we're going to measure the speed of sound in air through a phenomenon known as resonance. So the idea here is that if you consider some sort of oscillating system, so let's say you've got, here's some swing set, and you have somebody sitting on our swing here. Right? So this person is swinging, and let's say there's another person back here that's giving them some pushes, right? So just probably from experience, that if this person here just pushes at random times, then motion is never going to be very large, right? Because these points in time when the force is applied could kind of cancel out any of the kind of natural oscillation taking place. But if the pushes are timed so they have close to the same frequency as the motion, you can get large swings. Okay. And so this same phenomenon can occur with any type of kind of oscillating motion. And when we consider sound waves, they are in fact oscillations. So we can take a quick look here. So here is an animation of a traveling wave, which you can think of as representing our sound waves. And so you can see that red dot that moves up and down, that is a single point in the medium, and you can see that it is oscillating, right? It's going up and down. Sound waves are actually longitudinal waves, so the motion would be back and forth, but this is still an okay image and an okay picture to have just to see what's going on. So this oscillation can also be reinforced. So if you have something where you have kind of this natural frequency that is driving this motion, you can get a resonance phenomenon occurring, right? So we are going to observe this resonance in our sound waves. And the first thing that we're going to want to do is just kind of write down, based on this diagram here, we need to know, well, what is our speed of the wave? And to get the speed of a wave, we can say, well, the wave travels one wavelength, and we represent wavelength with the Greek letter lowercase lambda in one period. And we use a capital T to represent period. So if you just recall that, well, the speed of something is a distance traveled over the time. The distance traveled here is our wavelength, and the time is the period. And we also have this relationship between our frequency and period, and that's just that they are the inverse of each other. So then we can get that our speed is the wavelength times the frequency. So if we are using tuning forks, they give us the frequency. So a particular tuning fork will have a particular frequency with which it will resonate. And so you can listen. So here is the 512 hertz tuning fork. So a tuning fork will just produce waves at that single frequency because it is designed so that that is its natural frequency. That's what it wants to oscillate at. So that is going to be what we use to produce sound waves of a known frequency. And so if we know the frequency, we just need the wavelength. To get our speed. Okay, so we can then determine the wavelength through use of something that we refer to as a resonance tube. And this resonance tube is just a tube that we fill with water. It has a metal cup attached to it where there's a hose that runs between the cup and the bottom of the tube. And then by raising and lowering the cup, we can raise and lower the level of water in the tube. And this has to do with, balancing out the pressure difference at the two surfaces. So this tube, this resonance tube, let me switch over here. Okay. So this resonance tube is what we would call a closed tube. So a closed tube has one closed end. An open tube would have both ends open. The reason that we call the tube with just one end that is closed a closed tube is because if you have both ends of a tube that are closed, it's not set up very well for holding sound waves between it. So the condition here is that at our closed end, we have to have a node on our wave, right? So these are nodes here. And the reason for that is that the air molecules can't move, right? They're trapped against this end of the tube. So the air molecules can't move. So the sound waves, like I said, are longitudinal waves. So the actual particle motion is kind of back and forth like this. And so at this closed end, you can't have that back and forth motion because the particle can't move through that closed end. So that gives us the condition that we have to have a node at the end of our tube. And then on the open end, we're going to have an antinode. Okay, and that is because at the open end, of course, the air molecules can move back and forth quite freely. So they're going to experience the largest motions at that open end. Once you get outside of the tube, then you no longer are inside, so we don't really consider that. So the kind of first frequency, the fundamental frequency that we can support inside of a closed tube is where we have a node at our closed end, and then we just have between there and the end, we just get to an antinode. And so this has a frequency given by this equation here, so it's the speed of sound over 4 times the length. We can also write this as that the length is equal to 1 over 4 lambda 1. So that is our first wavelength. So you can see we have 1/4 of the wave. And so our length of our tube here at that point is 1/4 of the wavelength of this wave. The next frequency that we would be able to support in this kind of tube, we would have one node here. You go to an antinode, back to a node, and then back to an antinode, because we have to end on an antinode. And so this has 3 times the frequency of our fundamental frequency. And so what we can see, and then you can go up to this 5 times the fundamental frequency. And so what we can see is that we can only produce these odd harmonics in a closed tube. And so we can take our relation that we just wrote down here, and we can generalize it as L is equal to N over 4 lambda N, where N is equal to 1, 3, 5, and so on. Okay. So from this kind of relation, then, we can determine the wavelengths of these different waves, right? We just have to find at what length do we get a particular resonance. And when we have that length, then we can get our wavelength. So we can take this and we can say, well, that lambda N is going to be 4 over N times this LC. And here, this is a corrected length, where this L corrected is equal to the length of the tube plus 0.4 times the diameter of the tube. And so this just has to do with the specific nature of these kind of sound waves. So we have to take whatever length that we measure and add 0.4. And then we can plug that into our equation here, and we can get a wavelength. And if we have a wavelength and a frequency, then we can determine the speed by our equation up here. Okay, so for this experiment, what you're going to do is basically you're going to watch a video of the resonance tube. And then while you're watching that video, you're going to be listening for the point of resonance. And so this will sound like an amplification of the sound wave. So you'll hear the sound get louder at that point of resonance. So one thing to note is that some of these videos will start with me striking the tuning fork and then bringing it towards the top of the tube, which is where I had the microphone set up. So there will be this initial point where it gets louder just because the tuning fork comes in near the microphone. But after that is when you're going to want to listen and try to find, you're going to be listening and watching at the same time, so that you can record where resonance happens. And so this is going to be just reading off the L on the tube. So there's numbers on the tube. Those are centimeters from the top of the tube. So that is going to be the L as shown in our diagram here that you're recording. And then you will need to correct that length according to our formula up here. And then that will go into this formula to give you the wavelength. And then you will get the speed of sound. So that is the general procedure. Is just watching the videos and listening for those points of resonance. I did take the audio that I recorded and I amplified it quite a bit to hopefully make it quite apparent where the resonance happens, because it can be kind of difficult to hear sometimes. So you might have to watch the videos a few times and listen for that point where it seems to get the loudest. There's some of the videos have multiple points that you'll be able to listen to it over and over again. So just kind of listen for that and try to record the length. If you are very careful in doing this, then you should be able to get the speed of sound to within about 1% of the actual value. So you should be able to get it very, very close. You just have to be very careful and listen for that point where it seems to get the loudest. So I will end this video here, and on the page on Canvas you should be able to find all the information you need, including the diameter of the tube, the frequencies of the tuning forks, and all that information will also be there. So hopefully you can get this experiment done relatively easily. It shouldn't be that difficult. If you have questions, feel free to contact your TAs or me, and we will try to help you out.